Hi, I'm Christopher Moore, and today we're going to talk about the exciting subject of kinematics. Okay, kinematics might not seem that exciting, but imagine what would happen if your students could take real, authentic motion data and use it to understand all kinds of things. This is a giant rock found in Death Valley, California, called a sailing stone. You can see the trails that these stones leave in the dry river bed as they move across Death Valley. And we have actual data that we can use from authentic journals that students can dive in and understand the motion, learning all about their velocity, their displacement, their positions at different times, their accelerations, and even the forces acting on the stones. So let's learn how to use real data in the classroom to teach kinematics. So who am I? I'm a professor of physics at the University of Nebraska, Omaha, and I'm co-author of the curricula Experience Physics and Experience Chemistry. I'm also the author of the books Creating Scientists, Teaching and Assessing Science Practice for the NGSS, and Teaching Science Thinking, Using Scientific Reasoning in the Classroom. You can find me on Facebook, on Twitter, on YouTube, at Chris Moore Sci, or at my website, creatingscientists.com. Motion requires a change in position. A good way to measure a change in position with time is by using video. A video camera takes images at a defined rate, typically 30 images every second. Each individual image is called a frame. Individual frames can be layered on top of each other, producing a motion diagram, where a motion diagram shows an object's position at several equally spaced moments in time. The image we're looking at here is a motion diagram for a skier. Individual frames from a video of the skier are layered on top of each other. The edited image shows the skier's position at several equally spaced moments in time. We actually have motion diagrams for the sailing stones. They come from a recently published article in PLOS One, which is an open access journal. The figures that you're looking at here show the sailing stones moving across the racetrack playa in Death Valley National Park. Also attached to these stones were GPS trackers so that scientists could figure out where the stones' positions were at any given time, as well as being able to figure out their velocities and from that their accelerations and the forces that are acting on the stones. In this short workshop, we're going to show you how to get access to this data and then how to use it in your classroom so that your students can use authentic data to solve kinematics problems instead of just plugging things into equations that they don't understand. To simplify a motion diagram, you can model the object as a simple dot. A dot diagram is a motion diagram where the object of interest has been reduced to a single point. A key feature of a dot diagram is that the time step between each dot is held constant. The velociraptors shown here can be represented as a dot. Modeling the velociraptor's motion as a dot simplifies the entire motion diagram, keeping you from having to draw several velociraptors. The numbers and the subscripts for the times show the order in which the frames would be taken if we actually took a video of a velociraptor. The time step between frames and dots is constant. Right? And so what this is telling us is that equally spaced dots means that the velociraptor moves the same distance in each time step. So now we're at the interactive component of this workshop. The first thing I want you to do here in a minute is go to the website creatingscientists.com/sailingstones. At that website, there'll be a series of questions that we're going to answer as you go through the workshop. So in just a moment, when I tell you to go, you're going to go over to you're going to pause this video first and then go to a new web browser tab or window and open up that website so that you can answer this question before you go forward. What I want you to do is look at the motion diagram we have here of the velociraptors, as well as the dot diagrams shown on the screen. And then answer this simple question. Is this particular velociraptor moving with the uniform motion that we just saw, or is it speeding up, or is it slowing down? And so I want you to go ahead and answer that question now. So you're going to pause the video and then come back to me after you've answered. Are you ready? Pause. You've come back from answering the question about the velociraptors and whether or not they were speeding up and are slowing down. The pie chart that you're looking at here shows a selection of answers from that question from faculty and teachers and high school teachers from across the country. All right? And so we see a large majority of people are saying that looking at this dot diagram and this motion diagram, the velociraptors are speeding up. And here's something really interesting about the dot diagrams, because they give us a lot more information than just a couple of dots and the positions at any given time. If we connect the dots with vectors, arrow vectors we call velocity vectors, right, then that's exactly what we find. We find that the arrows in between the dots can represent the velocity at between any given time intervals. Right? That's a real good power of these dot diagrams. And so we can see that V1 is smaller than V4. And so what that's showing is that the velocity is getting larger with time. So as the dots start to spread out, the velociraptor is speeding up. Similarly, if we saw the dots starting to compress, then the velociraptor would be slowing down. You and your students can convert a dot diagram into a graph of position as a function of time, called a position versus time graph, or more simply, just a position graph. The straight line motion that we're seeing in this position graph shows that the position changes the same amount in each time step. We call this type of motion uniform motion. To get the position graph from the dot diagram, we take the dot diagram and we've rotated it such that it aligns with the position axis. The time step between the dots is used to generate the scale on the time axis. And again, the arrows between the dots in the dot diagram can either represent displacement vectors, or because the time steps are uniform, they can also represent velocity vectors at each given step. So therefore, you can see that the displacement changes the same amount in each time step, and the velocity is going to change the same amount in each time step for uniform motion. Now that students have constructed a position versus time graph, they can use that position graph to get more and deeper information. In this case, they can look at the slope of the position graph, where the uniform motion results in a linear graph. That slope of that line is the velocity, the average velocity of the object as it moves throughout space. The steeper the slope, the greater the velocity. So now they can compare the motions of two objects either by using their dot diagrams or by converting those dot diagrams into graphs and looking at the slopes of the graphs. So let's talk about what we've done here. We've had students start off by making concrete motion diagrams that they can recreate on their own by acting it out even. And then we've taken that concrete motion diagram and had them convert it into a slightly more abstract dot diagram, where they're starting to be able to pull out very useful information like the displacement with time and the velocities. And then finally, we went to an even more abstract form of representing the motion by turning the dot diagram into a position diagram and learning how we can use those in order to get even more interesting information. What we're doing is we're going from concrete to abstract representations, because knowledge in physics is often in a symbolic form, and those symbols must be combined and converted via sets of rules. The human mind relates best to picture-like representations that emphasize qualitative features as opposed to quantitative features. And so for students to learn symbolic representations, we have to link the abstract to the concrete representations. And what that requires is for your students to be able to go backwards and forwards from different representations of the same phenomena, in this case, just uniform motion. Being able to think in terms of a graph, right? And then going back and making that into an actual motion diagram or acting out the motion. And then going the other way. And then here in just a second, we're going to talk about how we can link that sort of concrete understanding to the mathematics. But we can't really understand the mathematics without having first that concrete picture. So now let's talk about turning that graph into mathematics. Your students can use a position graph to write a mathematical equation for the position as a function of time for the uniform motion. From the Common Core, they already know that the generic equation for a line is y as a function of x equals mx plus b, where m is the slope and b is the y-intercept. When the position graph is also a line, you can write this generic equation in terms of the specific variables for initial position, final position, velocity, and time. Similarly, your students can go the other direction and sketch a position graph when they're provided the mathematical equation for the position as a function of time. So your students will be able to convert graphs to math and maths back to graphs. Your students can now convert that position graph to a velocity versus time graph. And for uniform motion, it's actually very simple because it just is a flat, straight line. Information can also be obtained by analysis of this velocity versus time graph for the uniform motion. The area under the function and between two times is equal to the displacement during the time period. The area is defined from the function to the t-axis. Where the function is above the t-axis, the area is positive, and when it is below the t-axis, the area is negative. When comparing the mathematical equation derived using the position versus time graph to the mathematical equation derived using the velocity versus time graph, keep in mind that d represents position and delta d represents displacement. The area under the curve does not tell you about position, only the displacement. Now let's go back to the sailing stones phenomena. We've taken a selection of the data from that peer-reviewed, authentic journal article and simplified it a little bit into the velocity as a function of time graph that you see here. By the way, if you go to creatingscientists.com/sailing, you can actually get this data. We have it there for you in a Google Sheet that you can download and use in your class, the simplified version. And of course, you can always get the raw data from the journal article, which we've also placed a link to in this website. So what I want you to do now, this is again the interactive part of this workshop, is go to that website, and here in a second when I tell you to pause, you're going to go there and you're going to answer the next question. And that is, what is the displacement from 2 to 5 minutes from this graph that we're looking at here? All right, are you ready? Pause. And now you're back from answering that question about the displacement from 2 to 5 minutes. So you've come back from the website, and of course you've seen how your students can use this authentic data from GPS units attached to our sailing stones, that anchoring phenomena that we've been discussing. Right, so you've been able to look at the 2 to 5 minute period, and you've noticed that the velocity is constant. That means that it's uniform motion, and we can find the area from 2 to 5 minutes by just finding the area of this rectangle. Right, which is just the base times the height. In this case, 6 meters per minute times 3 minutes, or 18 meters of total displacement. And that leaves, of course, the triangular piece here, which is non-uniform motion, that we're going to talk about here in a second. So let's reflect on what we've done here for a moment. we've taken actual authentic data from a journal article, and we've got our students analyzing the motion, looking at the velocity as a function of time graph and being able to figure out the displacement, how fast the object is going, the rocks are moving, right? All of this great information. And we haven't really done a lot with equations. And the little bit we did do with the equations was creating those equations from the data. So imagine how powerful this is. You can now take, say, a motion cart or one of these collision carts that can collect position as a function of time with a wheel sensor as an example. And they can move these around in a lab and get actual data and analyze that data instead of just relying on an equation that they may or may not necessarily understand. It's really powerful to use data to get these ideas as opposed to just giving them a way of solving an algebraic equation. So now let's look at non-uniform motion. Remember those velociraptors? The velociraptor that had its spacing increasing with time? That was the very first interactive question. And that was an example of non-uniform motion. So your student can get a good mental model of that, and they can maybe sketch out a motion diagram and then convert that motion diagram into the dot diagram that we see here. Once again, we rotate that dot diagram and we can create a graph of position as a function of time. The unequally spaced dots indicate this non-uniform motion, and that results in a curved position graph as indicated here on the picture. So you can see that the displacement is decreasing with successive time intervals, indicating that the object is slowing down. With uniform motion, we saw that the position as a function of time graph was a straight line. However, with non-uniform motion, and in the particular case of what we call constant accelerated motion, it's the velocity as a function of time graph that becomes a straight line, because we just saw a curved shape for our position as a function of time. So the constant accelerated motion results in this linear velocity graph, and the slope of that line is the acceleration. And so we can see that steeper slopes lead to larger accelerations. Now, we've added another representation here. This representation is the velocity vectors using the head to tail method from the dot diagram to show the direction of the change in velocity and therefore the direction of the change in acceleration. In our curriculum, we actually use this change vector notation quite often because we're always in physics looking at changes in velocity for accelerations, right? We'll be looking at changes in electric field directions, changes in magnetic field directions, elevators going up and down and slowing down and speeding up. And it's really those change vector representations that allow the student to really comprehend the directions of the accelerations that are happening. So once again, because we have a sloped line, right, we can use that generic line equation, y equals mx plus b, to write a mathematical equation for the velocity as a function of time, right? Because now we have the data for velocity as a function of time, and for constant accelerated motion, it's linear. So the y equals mx plus b general generic line graph can be translated into that velocity graph, and then from that we can get the first equation of motion, v equals the initial velocity plus at. And now, just like we did for uniform motion, we can look at the graph of velocity as a function of time for constant accelerated motion and use it to write another equation for the displacement as a function of time. In this case, it's a little different, right? Because it's not a flat line. We have a sloped line. So the area under the curve is actually the combination of a triangle's area and a rectangle's area. But if we actually look at the base times the height of the triangle and multiply it in half so that we get the area of the triangle, and then we look at the base times the height of the rectangular piece and we add those two components together, we actually find that the displacement is equal to the sum of those two areas, right? And we get the second equation of motion, that the displacement is equal to the initial velocity times time plus half at squared. Right? So what I want you to think about is the fact that we started with data, and from there we managed to get the two equations of motion. All of the other equations of motion that you would deal with in a physics course are just derived from these first two. But your students are generating the equations from the data and the graphs. Now this brings us to our final interactive component of this workshop. So once again, in a moment when you pause the video, you're going to go to creatingscientists.com/sailingstones. And at that website, you'll answer that final question using that real data that we've taken from that publication. All right, for the sailing stones, that's the anchoring phenomenon. All right, now again, we have a velocity as a function of time graph. It's that same velocity as a function of time graph, but now instead of looking at the non-uniform motion component, we're going to look at that first 2 minutes. And you're going to tell me what the displacement is from 0 to 2 minutes, where the stone started from rest and then it reached a speed of about 6 meters per minute before it began to go with uniform motion across the dry riverbed. So in just a second, you're going to pause and go to creatingscientists.com/sailingstones and answer this question. Are you ready? Pause. So now you're back from answering that question, looking at the sailing stone's motion from 0 to 2 seconds. And this is constant accelerated motion, so the velocity as a function of time graph is linear with a defined slope. So we can look at the area under the graph and determine what it is that the displacement happens to be. Now in this case, since it started from 0, we don't have that rectangular piece. It would just be the half AT squared, right? But we can also look at it as the base times the height times that half. Half 2 minutes times 6 meters per minute equals 6 meters. Now what's really interesting about this is your students are doing integrals. By looking at the slopes and by looking at the areas under the curves, your students are doing time derivatives and integrals. That's calculus. But they don't have to know that they're doing calculus, or sometimes you can even tell them that they're doing calculus, thinking about how it's going to set them up for the future because they understand what it is that they're looking at. They also know where that half comes from in the half AT squared. It's not a mystery now. It is coming from the area under the curve. And we have a triangle, and so that half comes from the area of a triangle. That's exciting and really powerful information that your students can use. And what's even better about this is it doesn't have to be a straight line or a flat line. It could be any weird shape or curve, and they can estimate the area under the velocity as a function of time graph. So you can give them really complex data, and they can use that to figure out what is the acceleration at any given instant as an example, as well as looking at the area or estimating the area to figure out the displacement. So here are the big ideas. Students must learn to represent physical processes in multiple ways and learn to convert those physical processes from one representation to another in any direction. This helps students make connections between the concrete ways of representing, such as pictures and graphs and the mental models they have about motion, and the more abstract ways of representing motion, such as graphs and mathematical equations. This helps students to group information into bigger units that we call, or that educational psychologists and cognitive scientists call chunking. That allows them to process large amounts of information at once. The mind can hold about 5 to 7 chunks of information. When experts with years of experience manage to group those small ideas together into larger and larger chunks, their 7 chunks actually become much bigger. They hold more stuff. But your students have to work through that process to be able to chunkify everything. And it really helps to go through the different types of representations to do that, right? Because each chunk for the novice is small. So as a reflection, what have we done here? Well, we've started with our students just taking motion and breaking it up into frames, right? And thinking about the motion that they could either act out or that they can draw little sketches of the actual objects, and then abstractifying those by making them into dot diagrams. Then they create graphs from those dot diagrams. And looking at those graphs of motion, they're able to then come up with mathematical representations and mathematical equations. And then that's really powerful, right? Because we saw where we can take authentic data and use that data to understand the motion of the object, right? Without having to resort to the equations of motion or moving around V's and A's and T's in just a random order. We don't give them problems with just a couple of the letters that they don't know and maybe one of the letters that they do, and then they go about solving algebraically. No, we give them rich, authentic data. Data that they can use to answer actual authentic research questions. And that's the big idea about having your students go through the multiple representations of motion to understand motion and understand kinematics. So I want to thank you for joining me today and remind you that if you go to creatingscientists.com/sailingstones, we have the Google Slides for this presentation there. There'll also be a recording of this presentation so you can watch it again. The paper, the actual article where we get all of this rich data for our sailing stones, as well as our simplified data that we use in the classroom. And then finally, there's one more question that I want to ask you that you can answer at that website. And that's taking this actual rich data from the paper and thinking about how you could get this into your classroom, right? Actually taking this actual velocity as a function of time graph and putting it into a lesson and having your students estimate the acceleration from, say, 0 minutes to 3 minutes, and then determining what the stone's displacement is during that time. Right? How exciting would it be to be able to take that actual data and have your students actually understand the kinematics of these sailing stones? So once again, thank you. I've been Christopher Moore this entire time, and I am one of the co-authors of the curriculum Experience Physics. So thank you again, and visit the website to get contact information if you want to reach out.